Hello and welcome to this video. In this video we will have a look at this nonlinear system, determine all its fixed points and their stability types, and after that we will sketch the fixed points in phase space and add some trajectories. For that we have all the formulas and definitions that we need here on the left. So let's actually start with the task. First we want to find all the fixed points of our nonlinear system. And if we take a look at the gray box on the left, we know that the fixed points occur where x dot is 0 and y dot is 0 simultaneously. That means for our system, x dot equals x times 3 minus x minus y has to be 0, and y dot equals y times 2 minus x minus y has also to be 0. In our case, we don't have to perform any complicated zero determination, we can just read off the fixed points. They are at 0, 0, 3, 0 and 0, 2. Now that we have the fixed points of our system, we want to determine the stability type for each of them. For that, we will use the Jacobian matrix. The Jacobian matrix is a matrix where the entries are partial derivatives of x dot and y dot with respect to x and y. So let's build all the derivatives. Now that we have the Jacobian matrix for our system, we can begin to analyze the stability of the system. To get the stability types of all fixed points, we evaluate the matrix at these fixed points. So let's start with F1. We find the matrix 3, 0, 0, 2, and we want the eigenvalues of this matrix. Now here it's actually quite easy to get our eigenvalues since it is a triangular matrix and we can just read off the eigenvalues. So now we have determined the eigenvalues, but what should we do with them? If we have a look at the gray box, we remember that we can use them to determine if a fixed point is a node or a saddle point and if a node is stable or unstable. And in our case, the determinant is positive, so we have a node. And the trace is also positive, which means that F1 is an unstable node. For F2, we will do this exact same thing again. We find the matrix minus 3, minus 3, 0, minus 1. And this matrix is also triangular, so we can read off the eigenvalues again. After that, we have a look at the determinant, which is positive, so F2 is also a node. To determine the stability type, we calculate the trace, which is negative, so we have a stable node this time. Let's do this one last time. For F3, we find the matrix 1, 0, minus 2, minus 2. The matrix is again triangular, so we read off the eigenvalues. Since the eigenvalues have different signs, the determinant is negative, which means that F3 is a saddle point. Now that we have the stability types for each fixed point, we want to sketch them in phase space with some trajectories. So let's start with the first fixed point. F1 was an unstable node at 0, 0, and we indicate that by an open circle in the phase space. To add the trajectories, we have to compute the eigenvector corresponding to the eigenvalue having the smallest absolute value. So F1 has the eigenvalues 3 and 2, so we compute the eigendirection for lambda 2, which is 2. For that, we can use this formula on the left, which leads to this linear system. And from that we can deduce that multiplies of 0, 1 are eigenvectors. With help of the eigenvector we can add some trajectories in phase space. And because it is an unstable node, they will tend to diverge from the node along the eigenvector, which looks like this. So let's have a look at F2. F2 was a stable node at 3, 0, and we indicate that by a black circle in the phase space. To add the trajectories, we compute the eigenvector corresponding to the eigenvalue having the smallest absolute value, and F2 had the eigenvalues minus 3 and minus 1, So we compute the eigendirection for lambda 2, which was -1. We used the same formula as we did for f1, which leads to this linear system. And from line 1 we can deduce that multiplies of -3/2 1 are eigenvectors. In our case we choose -3, 2 as eigenvector because it is easy to work with. Now we can add some trajectories, and this time it is a stable node. So they will tend to converge to the node along the eigenvector, which looks like this. The last fixed point was a saddle point, so we draw an open circle in our phase space at 0, 2. Because it is a saddle point, the trajectories will approach along the negative eigenvalue and diverge along the positive eigenvalue. So let's compute the eigendirection for lambda 1, which was 1. We get this linear system where we can deduce that multiplies of -3/2 1 are eigenvectors. We want to have numbers that are easy to work with, so let's choose 3 - 2 as eigenvector. We compute the eigendirection for lambda 2, which was -2. We get this linear system. We can deduce that multiplies of 0, 1 are eigenvectors. We have found both eigenvectors, so we can add some trajectories around f3. Because it is a saddle point, they will approach along the eigenvector 0, 1 and diverge along the eigenvector 3, 2. Now we have plotted all fixed points with some trajectories, and one last thing that we will do is to put everything together and try to connect the trajectories to infer the whole phase portrait. If we have done this, the phase portrait might look like this. And with this, we have already finished the task, and we hope that you enjoyed watching this video. If you have any questions, don't hesitate to ask.